Welcome back to the second video about magnets and their magnetic fields. We are still discussing permanent magnets in this chapter, and in the last video we've discussed briefly how magnetic effects like the aurora borealis can occur when you have interactions between different magnetic particles. Now in that video we saw that the Earth has a magnetic field of its own, and that magnetic field is used to deflect those gases. There are two shapes of magnetic fields that you have to know by heart. We will be limiting ourselves to the different fields of both bar magnets and horseshoe magnets. Now this isn't easy to do with a mouse on a screen, but bear with me. If you have a bar magnet like this one here, if you want to sketch the magnetic field, you will first have to decide whether it's the North Pole left or the South Pole right. You can of course reverse this, but for this first exercise I will draw these. If you have to create or sketch the field lines of these, and you have to be able to do so yourself for a lot of the exercises coming along, the first line you start off with is the center line that essentially runs like this, in line with the actual magnet. Then you start off at the corners and you go around in sort of a nice sweeping motion from one side to the next. And then you start going down the side of this magnet and do the same on this side. Now, of course this is quite difficult to do, and I will show you a better version soon. And you have to repeat this. I won't be closing these, but you can imagine that they go around all the way here and back here, these field lines as well. You will have to repeat this motion essentially at the bottom part of the bar magnet as well. And this creates, or this shows, the shape of the magnetic field of a bar magnet. Now these are just the field lines in this case. These field lines will have a sense. Much like electric field lines had their sense, magnetic field lines will have it as well. The rule is, the field lines, they are pointed away from the North Pole, and they will be going towards the South Pole, like this. So if, at the start, I had swapped the poles around, it wouldn't make a difference to how the magnetic field lines, the pattern would look, but the sense of the field lines would be reversed. Now, like I've said, field lines arrive at the South Pole and they will arrive here. Now, if you want to know how strong the magnetic field is roughly, a good guideline is checking the density of those field lines. And as you can see, the field is strongest near the poles, because the magnetic field lines will be the most dense in that area. This is of course incredibly analogous with what we've seen with electric field lines. Now I'll be swapping color because there will be a bit of overlap when we're doing the horseshoe magnet. The horseshoe magnet is, or has, a polarity, with one leg being the North Pole, the other being the South Pole. Why do we use this one? Well, in between the two legs of the horseshoe magnet, you will get a nice even spread of field line. They will be perfectly parallel and evenly spread out. We've seen this in the past. This is a homogeneous field created in between those two legs. Now on the top it will just go around looking quite similar to the top half of the bar magnet. So they will go sort of bend around like this. Now this isn't necessarily the interesting part, or the reason why you would use a horseshoe magnet. You mostly do it for that homogeneous field in between. So that's the first thing. Now a few things to note. Even though we're using different colors to show you what North and South Pole is, like I've said in the previous video, that is just paint. If we, for example, take this exercise and you break a magnet in two parts, what will the end result be? Of course your paint won't rearrange, but you would end up with situation C. You would just end up with a smaller magnet with its one side being considered North Pole and the other side being considered South Pole. Same with this bit, it will just be two smaller magnets, each with their own polarity. So this situation would represent the polarity of the two new magnets you've created best. And also the next exercise, if you bring a positively charged object near a compass needle, which situation is correct? The magnet will be attracted to the charged object, will be repelled by the charged object, or nothing will happen. Well, in this case, seeing how this would be a magnetic field interacting with an electric field, nothing will happen. Even though electricity can cause magnetic fields, can create magnetic fields, they will not interact with each other. So don't confuse electrostatic fields with magnetic fields. They will not interact. And like I've said, there is a link though between magnetic fields and conducting wires. There is a man called Hans Christian Ørsted, which I'm not mistaken was a Danish scientist, who first discovered that a conducting wire has an electric field around it. He noticed that his compass needle was getting deflected, was changing direction when it was near a conducting wire. How did he do this? Well, I will show you a small animation as well, linked in the video description, so do check this out. But if there's no current passing through the compass in situation A, nothing will happen. As in, the compass needle will just be pointing towards the North Pole, as it should, like a compass should do. And its South Pole, of course, being in the opposite sense in this case. However, when he started having current going through the conductor, the compass needle will react to it. It will deflect. And how will it end up standing? It will sort of end up standing completely perpendicular to the tangent line in an imaginary circle around the conductor. So he noticed that every single time, no matter where he placed the conductor, the compass needle would deflect to become perpendicular to the wire. Form a sort of a cross in this case. Now, this isn't easy to actually draw, so we have to make a few arrangements beforehand before we go and draw this. Now, the first thing we do is create our straight conductor, in this case, well, straight. Now, if it has a current running through it, it will create a magnetic field pattern. Now, what will be the shape of this magnetic field pattern? Well, it will be concentric circles, meaning you will have a bunch of circles running around the object, around the conductor. This will happen at every single part of the conductor in this case. So you sort of get this cylinder of magnetic field lines going around the conductor, like so. To represent this. Now, the problem is, these field lines will also have a sense, and we'll be discussing this more in the next chapter. The reason why I've used full lines for one half of my circle and dotted lines for the other half is because these full lines represent the line that is coming sort of out of your paper when you're looking at it three-dimensionally, while the dotted lines are the circles going behind the paper, in this case, behind your sheet of paper. Now, why is this important? Well, if I want to draw the field lines on these, and I have to put an arrow on it, we have to assume that you always draw your arrowheads on the full line, the line coming out of the paper, the line that is aimed towards you. Why? If people just start creating circles like this and then slapping an arrow on it, I don't know what direction this thing is going into. If you don't see my mouse moving first, right, it would look all the same in the end. And I can't grade whether or not you know this was drawn along or clockwise or counterclockwise. So this is the first thing we have to do. The first agreement we do is sense lines, arrows, always on the full lines and never on the dotted lines. Now, feel free to attempt these next few exercises, which I will be discussing with you in a short while. They are not super difficult. You can try them, use a pencil or something else you can erase easily if you're not entirely sure about them. And we will be discussing them next class. See you then.